Hey everybody, this is Larry. This is the third day of July, and therefore the third day of the July Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem. Max sum of rectangle larger than k. Okay, so I usually solve these live, and everything or if I'm Googling, you'll see it. So if it's a little bit slow, feel free to fast forward or watch on 2x or whatever, or skip ahead, whatever you need to do. So this one is going to be a little bit tricky. So the first thing I look at is the constraints to kind of see some ideas. Seems like we have m and n is equal to 100. So yeah, let's see. I mean, I think one of my advantages is that I've seen a similar problem before. I don't know if this is this one, but But this is a hard problem, to suffice to say. I think the first step that I would do is try to think about what happens if you. No, let's simplify the problem a little bit first, right? Let's start with a max sum of an array no larger than k. Then what can we do? Well, the thing we can do is we can do something that is that linear time? You can do something n log n by using prefix sum and then binary searching on the endpoints. Yeah, because is there a sliding window thing? I don't know if there's a sliding window thing, because the problem with sliding window in this case is that there are negative numbers, and with negative numbers, I don't know if the monotonically increasing property still holds. So like you cannot just move, because you may be able to move left, but you may take a subset of left, and then moving right will maybe give you a better answer as well. So that problem is a little bit tricky. But I do believe you can get n log n by, if you have a prefix sum array. Let's say you have some array. Let's just take the first. Okay, maybe a little bit longer. Okay, actually this is a one-dimensional array. But yeah, let's say you have something like this, and then you have a prefix sum of two, well, let's just start with 0, 2, 4, 3. And then for each one, you can binary search the closest number to k, or something like that, so that you can get it. For example, in this case, k is 3, so our k is equal to 3. So at 0, well, there's nothing to the left of it. We add it to a set. At 2, we want to search. Basically we are at some x, and we're looking for some y such that it is such that this condition holds, right? So that means that given x and given k, we can actually subtract k and then add y on the other side. So then we can do a binary search on x minus k in the prefix. Kind of. I don't know if that makes sense, because I think this obviously requires a prerequisite in prefix sums. So if you're not familiar with prefix sum, I know this is the third day. Sometimes I go over prefix sum of it, but in this case, I'm not going to go too detailed in prefix sum because I think this is a pretty tricky problem. So definitely practice out the prefix sum problems first. But basically the idea is that, okay, let's say we're at this 4, right? And we want to know some segment such that it ends at 4, and the sum of that segment is 3, right? So then that means that we want to binary search 4 minus 3, so for some number that's less than 1. You could play around with some binary search idea, but that's basically the idea, right? And here that we found the 0, so that means, because 2 is bigger, so if we found 0, that means that y is equal to 0. So in this case, we have 4 minus 3 less than equals to 0, that means that the sum in this case, wait, is that true? Oh, maybe I did it the other way around, sorry. Actually, you want to find 2, right? Because now you have, did I do the signs wrong? Did I mess something up? Dun, dun, dun. Oh yeah, no, this is right. I just kind of plugged in 0 sillily. And we want to maximize y in this case. Oops. And then now when you plug everything back in, you have the smallest sum, which is x minus, so 4 minus 2 is less than 3, where k is 3. So then that means that the largest sum is 2, which is the point that ends at 4, right? So I don't know if that is kind of a good way of explaining it, but basically you have some idea of maybe I can draw it out a little bit. Hang on. But yeah, that's basically the idea, is that, okay, so you have some prefix sum. Oh, I don't think I'm showing on screen. Hang on. Okay, for some reason that's, oops. Is that better? Okay. So yeah, so basically the idea is that, okay, you have some prefix sum, right? Where and this is like a pseudo number line or something like that. So for instance, we have 0, 2, 4, and 3. Basically, we're trying to figure out for a target where the sum of some line segment, it's going to be less than or equals to 3, but the closest as possible. And basically, from here, we dump all the previous numbers in something that we can binary search, either a set or whatever. And in this case, we can clearly find the 2 here. So that's basically the idea for the 1D case. And then the question becomes, okay, so we have an idea behind the 1D case, right? How do we generalize it for a matrix? I think for this case, given that m and n is 100, you can actually just do repeat the same algorithm, but for a subset rectangle instead. And what I mean by that is from brute force, because m times n, or sorry, m and n, like the raptor, because m and n are both 100, then that means that there are n, roughly speaking, 100 choose 2 possibilities. Basically, for example, because you can just basically choose any basically you can choose, let me change the color. You can choose an upper bound and a lower bound of the indexes. So basically that's your height of the thing, and then you can effectively treat that as a 1D problem and then do what we did before. And then we take the max out of those. Basically, we only look at this segment. For example, maybe we want to try j is equal to 1, and then the max j is equal to 10, say, right? So then now we kind of squeeze that, compress that in, and then try to do it that way. That's basically what I think I'm going to try to do. Thinking about the complexity for a second, this is going to be 100 cubed times log 100. So how much is that? 100 cubed is going to be about 1 million, and then log 100 is like another 10, so it's going to be about 10 million. Hopefully this is fast enough. Maybe we have to do an optimization, but yeah. And then the follow-up is, what if the number of rows is much larger than the number of columns? So in that case, notice that we did it, with the rows. You could just transpose the matrix so that you kind of basically flip it or rotate it or whatever you want to call it, so that you can take advantage of it as well, because it is going to be m times n times n times log n or something like that. And in that case, if you want to reduce log n to log m or log m to log n, then you could just switch the dimensions. Okay, so I think that's enough of an idea to let me get started. I know that the explanation is a little bit hand-wavy, a little bit tricky. Hopefully, the ideas are there enough that we can get started and yeah. yeah, hopefully that should be good enough. I'm just thinking about how to explain it. It's very tricky because I think it took me a long time to get this the first time I did it, like a couple of years ago. But with that idea, I think I might still be wrong though, to be honest, because it's a while, and I am solving these live. So yeah, okay. So let's see. So first, another thing that we have to do, I actually forgot to mention one bit. How do you kind of reduce this? How do you reduce this thing to a 1D problem, right? Well, the way that you would do it is by why is that not showing up? Why is that showing up a different window? Hang on. So basically the idea is that, okay, and this is part of prefix sum, which is why I forgot to mention it, but this is a 2D version of prefix sum, sometimes refers prefix matrix. So the idea here is that, okay, so to get an arbitrary sum of a rectangle, which we have in orange, we basically pre-calculate the sum from the corner, the upper left corner, all the way to that corner. And if we do that for every possible corner, then the orange box is just going to be equal to this yellow box minus the two green boxes, and then you add it back in the purple box because you double subtracted it. So that's basically the idea behind this problem as well. And from that, you can kind of compress that to 1D as you kind of move from left to right. That's basically, that's basically, I think, all the pieces we need, even if it's a little bit tricky. Feel free to maybe watch it again if you're having trouble, or just ask me a question on either the YouTube comments below or in Discord. Okay. So let's get started. Yep. So let's start with the prefix sum. I know that some people do it different ways, but I do it this way because I don't know, it feels more natural to me. But yeah, prefix is equal to times typing is hard, and I always have an extra 0 row and column to denote nothing, basically, right? Like if you don't use it, otherwise it's still not that bad, but you have to do if statements in a lot of places. So yeah. So now let's do the prefix sum. Whoops. Let's see. Well, let's do it this way. Plus matrix of x, y. Does that make sense? When I'm at 0, 0, no. Oh, no, this is right. Oops. Wait, am I? Man, off by 1's a hard. Okay, let's say we're at 0, 0. We want that to be 1, 1 into the prefix. So yeah, okay. But I think this is a little bit off because we want to do. Yeah, okay, doesn't really matter. And then I do another route. There are a couple of ways to do this actually, but I don't know. I find this more intuitive for whatever reason. Your mileage may vary, as I said. And then we can print it out just to kind of see real quick. And in this case, you have an extra padding of whatever. You have 1, 1, 2. 1, negative 1 should be the sum of the corner, which is or the little square, so that's true. And then 3 is the sum of all the things, so that's 2, 0, 3. So that's good. Okay. And then now we just do the brute force thing. Okay. So for let's call it top, is it, or maybe bottom, depending on how you want to go up or down. I don't know. Doesn't really matter though. Let's just call it x1 then. Rows or x2 in range of x1 rows because it could be the same column. Okay, yeah, that makes sense because you can have the same row. Just have to be careful about your indexes. But yeah, so then now we have to do set is equal to. Is there Python set binary search? I always forget whether you can buy Okay, so set doesn't allow you to do binary search, so we'll just use sorted list for now. Basically, a sorted list is, at least in Python, a sort of a tree type thing. It's not quite true. There are some nuances, and you should read about it if you're really interested in it. But basically, it's a data structure that keeps a sorted list, which is what it sounds like, and adds stuff in, roughly speaking, log n time. And you can do binary search on it because it's sorted. Yeah. So then now, how do we do this? So now we're given these, now our height is x1 to x2 inclusive. So, okay. And now we're trying to go from left to right. Okay. So for y in range of, yeah, from 0 to columns. Okay. What do we do? So, okay. So the current prefix sum. What is the current prefix sum? The current prefix sum of this is going to be, so x2 is the larger number. So the lower right corner is going to be something like, yeah, this plus 1 because we have to take a count off by ones. So that's the lowest corner. And then we have to subtract that from, as we said, now in this case, I'm just trying to think about how to do it, but in this case, we only have to subtract the difference between x1 and y, right? Because we're just subtracting the columns, or not the columns, but the upper part of that rectangle. If you want me to visualize it back, here you go. Basically, right now, what we are doing is we want to, let's say we have, this is x1 and this is x2, and then basically we want to look at the sum of this chunk, so which is equal to the sum of me changing colors, which is, oh, that's not a box, which is basically this minus this, right? So we don't, so I think that's actually a different but also still easy-ish formula, which is what I did actually. So yeah, I think this is it for the current prefix sum. And then we try to binary search from this. Bisect left. So we have, as we said, current minus some previous less than or equal to k. So then we minus k plus, so minus k is less than some previous. And we want to maximize this number. Wait, is that right? Did I mess that up? No, we want to minimize this. We want to minimize this number so that this, we want to minimize this so that this is maximized, right? Because we're trying to max current minus previous, and the way that we do that is by minimizing previous. So we want to minimize previous for which this is true. So, okay. So target is equal to current minus k. That's so, because when we're trying to get the smallest, bisect left should be good. Yep, okay. Target, so now this is the current index. If index is within length, otherwise it means it's out of bounds and we don't find a number, then S of index is the smallest number that's bigger to, So then that's the number that we're looking for. That's the previous. So then current minus this previous is a target answer. So then let's keep track of the best answer. Can it be negative? Maybe it can be actually, but max sum, because k could be negative as well. So okay. So actually this should be, say, negative some big number. Okay, so then here we just do this, and I think that should be okay. And then at the very end, we want to add to the sorted list the current prefix sum. And that may be roughly it. Might not be correct, but I think conceptually that's it. Maybe I'm missing some weird stuff. But let's test some test cases. Isn't sorted containers? What did I write? From sorted containers. Oh, containers. Okay, so this looks mostly good, but it's not though. At least it runs, but so this finds. Okay, so at the corner 3 and k is equal to 2, it tries to find 1, and instead it finds. What does it find? Okay, it's time for some debugging. I might have some off by ones because it's very. Oh, actually, this is an off by 1. This should be y plus 1 because maybe that's why. Okay, let's run it again. Okay, I mean, maybe it's better, but this case is clearly not better. Dong dong dong. You think? Because this one should be pretty straightforward in theory. So we have closest to, wait, or maybe I'm thinking it wrong. No, that should be right, maybe. Expected answer is 3 when you have all 3, and the answer is 3 at the end, and we should be able to binary search for 0. Oh, because I don't add 0 as in the binary search for having no elements in the beginning. Okay. Okay, so this looks good. To be honest, not gonna lie, I'm not super confident about it, but this video is already 22 minutes in, and it's late at night, and I'm a little tired, so I'm gonna hit YOLO submit and then see what happens. Hopefully it's fast enough, because that's the other concern that I might have. Okay, cool. So this is fast enough. I do wonder. I think that. Okay, let me think about it for a second. What I want to say. Yeah. So this is good. This is, instead of using M and N, because I always confuse about what's M and what's N. Let's use R and C. So in terms of space, you can see that we use O of R and C space and prefix, and in theory, assuming that we always free our memory, this is only going to be O of C, so this is O of R times C in space. In terms of time, this is O of R times C, as you can imagine, and as I said, this is O of R choose 2, which is R squared roughly, times C, so R squared C times log C. So R squared C times log C, well, R squared C times log C. Oh, that's a mouthful. Let me just write it out then. It is the complexity. And of course, if R is way bigger than C, you just, like I said, transpose the array so that you get the smaller number on the square part. Yeah. Let me double check that. Oh no. I think I do this very often, but I forgot to do it. But that's fine. I think I didn't really change anything after displaying that. But yeah, so to go over it again, because I covered the code because I'm an idiot. This is what the thing that was in the picture that you stared at for a while because I didn't unblock it. So the target is current minus K. And what I said, and hopefully that came through, even though I think that this was blocked. So we have this where we try to maximize this, which means that we want to minimize previous. So yeah. So that's basically what we did by getting the smallest previous that is greater than target, right? Because that's basically, this is the target and we're trying to get the smallest number that's bigger than it. Bigger than previous, right? And then if this is found, then we do this best thing, and then at the end we add it to a set so that or sorted list so that we could search for it later in a binary search kind of way. And of course, in other languages you may use tree or something like that. Yeah, that's basically what I have. Let's peek over the solutions real quick, because I wonder if there's an m or r squared times c solution. I feel like there may be, but I'm doing it a little bit funky way. Oh, this is actually the way that I did it. Huh. That's kind of cool, I guess. Yeah, and this is what I set. What? How is this? Oh, I guess you can do it that way. That's a little wacky, though. Oh, the follow-up is whatever. Combining with contain. There's a contains album? Oh, no, that's the same thing. Okay. Same idea. Okay. Well, I think I'm happy with my solution. Let me know what you think. Let me know if you have any questions. Come on Discord or whatever, leave a comment in the thing below. I think my code is relatively clean as well, and I am solving it live, so I'm happy about it. I mean, there's some like maybe minor constant thing and space. So it turns out that the thing you can notice is that we always use this thing, so you can actually pre-process the array differently, but I think it's fine. Yeah, so that's all I have for today. Hope y'all have a great weekend. Happy 4th of July if you celebrate it. And yeah, stay good, stay cool, to good mental health. I'm gonna do some contests later. Good luck, and we'll do it together. Later. Bye bye, and to good mental health. Bye bye.